Good day everyone. Today I will be discussing the free vibration of single degree of freedom systems as part of the course Me22088. My name is Dr. C. Sendamarikana and I am an associate professor in the Department of Mechanical Engineering at SVC. In this slide, we will explore different types of vibrations that can occur in mechanical systems. Let's start by understanding the free vibration. Free vibration occurs when a system oscillates only under an initial disturbance with no external forces after the initial disturbance. For example, imagine pulling a mass attached to a spring and then let it go. The system oscillates freely at its natural frequency. Undamped vibrations are happens when the system oscillates without any resistance from the surrounding medium. This means the amplitude of motions remains constant over a time. A perfect example of this would be a spring mass system oscillating in a vacuum when there is no air resistance to damp the motion. On the other hand, damped vibration occurs when the amplitude of free vibration diminishes gradually over a period of time due to resistance offered by the surrounding medium such as air. As the system oscillates, the energy will last to the medium, causing the amplitude to decrease until the motion eventually ceases. Many mechanical systems and structural systems we encounter in engineering, despite their apparent complexity, can be simplified and analyzed using a fundamental concept, single degree of freedom systems. Think of this way. We can boil down the behavior of a system to just one essential variable, how it moves in a single direction. This is incredibly useful because it allows us to understand the basic dynamics at play without getting bogged down in intricate details. Consider this general representation. We have an equivalent mass which represents the total mass of the system concentrated at a single point. This mass is acted upon by forces causing it to move. Now, let's make this more tangible. Here we see the iconic Space Needle. While it is a complex structure for certain type of analysis, we can top and make it as a single degree of freedom systems. We can imagine the entire mass of the tower get concentrated at its top and then consider how it sways back and forth in one direction. This simplification is illustrated in these diagrams. On the left, needle as a tall structure with a certain stiffness. On the right, we have the classic spring mass system. The archetype of single degree of freedom model, the K value represent equivalent stiffness of the structure, how much force it takes to displace it. In the case of the Space Needle, stiffness depends on its material property, geometry, specifically related to how the length of the structure cubed impacts the overall stiffness. Stiffness formula, as we know, K equal to 3 Young's modulus I, that is moment of inertia, divided by L cube. This equation shows the relationship between the stiffness, modulus of elasticity, moment of inertia, and length of the structure. By representing complex systems like Space Needle as simple spring mass models, we can use well-established equations and principles to predict their behavior under various loads and conditions. This is the power of the single degree of freedom idealization, providing valuable insights through simplification. Let's delve into how we actually derive the equation of motion for a single degree of freedom system. We will start with a fundamental principle, Newton's second law of motion. As you know, this law states that the force acting on an object is equal to the mass of the object and multiplies with its acceleration. Mathematically, we can express it as F equal to mass into acceleration, where m represents mass, a represents acceleration. How do this apply to a spring mass system? Here, we see a more precise form of Newton's second law, suitable for systems where mass might change over time. F of t represents the force acting on the mass at any given time. The term dx, that is the velocity with respect to time, differentiated with respect to time, otherwise changes the period of time, then we can call it as acceleration. So we are essentially saying force equals mass into acceleration, but in a calculus form that allows for more complex scenarios. Now we assume that mass is a constant, which often the case. This equation simplifies considerably. We get f of t equals m times the second derivative of displacement with respect to time. This second derivative is the acceleration, represented more concisely as x double dot. Now, let's expand our discussion of equation of motion to include both rotational systems and a specific type of translational system, the undamped single degree of freedom systems. First, let's consider rotational motion. Just as force causes linear acceleration for rigid body rotating about a fixed axis, Newton's second law takes the form as shown in this equation, that is m of t represented resultant moment or torque acting on a body at a given time. J is the mass moment of inertia, which is the measure of the body's resistance to rotational acceleration. Theta double dot is the angular acceleration, the rate of change of angular velocity, and theta itself is the angular displacement. So this equation tells us that the torque applied to a rigid body is equal to moment of inertia multiply the times of its angular acceleration, that is t equal to I into theta double dot. Now shift our focus to translational motion and a crucial concept, that is undamped single degree of freedom system. Undamped means we are ignoring any energy dissipation due to friction or other resistive forces. This is an idealized scenario, but it is useful starting point for analysis. Simply F equal to ma to a mass m in an undamped single mass freedom system. This equation can be written in two equivalent forms. First forms, that is f of t equal to k of x, shows that force acting on the mass is proportional to the displacement and is always directed opposite to the displacement. This is the restoring force provided by the spring. The force is also equal to the mass times the acceleration. The second form, mx double dot plus kx equal to 0, is the standard form of equation of motion for an undamped single degree of freedom system. It has tells that the sum of initial force and restoring force is always zero. These two equations 2.2 and 2.3 for undamped translation are fundamental to understanding the behavior of a wide range of mechanical and structural systems. They relate the forces and moments acting on a body to its relating motion, either rotational or translation. Let's discuss the equation of motion using D'Alembert's principle. By utilizing D'Alembert's principle, the equation of motion can be reformulated considering the two equations for motion given as f of t minus mh double dot equal to 0 and m of t minus j double dot equal to 0. Applying D'Alembert's principle to a system, we derive the equation of motion such as it is going to be minus kx minus mh double dot equal to 0. Otherwise, we can rewrite mh double dot plus kx equal to 0. This equation fundamentally describes motion of the system under the influence of forces and moments applied to it. We have seen in the previous slide how to derive the equation of motion using Newton's second law. Now, let's explore an alternative approach, principle of virtual displacements. This principle offers a powerful way to analyze systems in equilibrium. The core idea is captured in this statement. The statement is, if a system that is in equilibrium under the action of a set of forces is subjected to a virtual displacement, then the total virtual work done by the forces will be zero. Let's break down. Virtual displacement refers to an infinitesimally small imagined displacement of the system from its equilibrium position. It's not a real displacement, but a thought experiment to help us understand the forces at play. Virtual work is the work done by each force during this virtual displacement. Consider our familiar spring mass system. Imagine the mass is displaced by a tiny amount, del x, from its equilibrium position. We have two forces acting on the mass, spring force and the inertia force. Note that inertia force appears as an external force in this context. Thanks to D'Alembert's principle, it's crucial to understand that the direction of virtual displacement is considered positive in the same direction as the positive x-axis. Now, let's calculate the virtual work done. Virtual work done by the spring force is nothing but del Ws is k of x into dx, that is stiffness of the spring into the infinitesimally small displacement. Similarly, work done by the inertia force is minus mx double dot into dx, that is the virtual displacement. According to principle of virtual displacements, total virtual work must be zero. Therefore, sum of this del Ws plus del Wi should to be equal to 0. Since del x is non-zero, we can divide it out, leaving us with the equation once again, the same equation of motion what we derived in the last slide. That is, this 2 will lead to mx double dot plus kx equal to 0. As discussed in the previous slide, let once again conclude that the total virtual work done by all the forces is set equal to 0 that we obtain, that is initial forces minus the stiffness force equal to 0. Since del x equal to 0, not equal to 0, then mx double dot plus k of x into del x equal to 0 means the remaining part mx double dot plus kx equal to 0 represents total virtual work set to 0. Notice that both terms include virtual displacement del of x. Let me explore the principle of conservation of energy, third powerful approach for deriving equations of motions. Principle is based on fundamental concept energy cannot be created or destroyed, only it is transformed from one form to another form. A conservative system is the one where energy is not lost due to friction, heat, or any other dissipative forces. In such systems, the total energy remains constant. This means that if we don't add or remove energy from the system through external work, the total energy, which is typically kinetic energy and potential energies, stays the same. We express this mathematically, that is potential energy T represents kinetic energy of the system and U represents potential energy. Another way to state this is the time derivative of the total energy is zero, meaning the total energy isn't changing over time. Principle of conservation of energy offers a powerful and often simpler way to derive equations of motions for conservative systems. It is particularly useful when dealing with systems where energy transformations are easy to express. Now let's apply it to our familiar spring mass system to derive its equation of motion. Remember, the principle states that the total energy of conservative systems remain constant. For our spring mass system, total energy is the summation of T plus U. T is given by half mx dot square, where m is the mass, x dot represents velocity. This term represents energy stored in the motion of the mass. The potential energy U stored in the spring is given by half kx square, where k is the stiffness of the spring and x is the displacement. This term represents energy stored in the deformation of the spring. Now we substitute these expressions for kinetic and potential energy into our energy conservation equation. Then it will become as half mx dot square plus half kx square equal to 0. Taking the time derivative, we apply the chain rule. Then with respect to time, we can get m x dot x double dot. The derivative of kx square will become as kx x dot let me see that both the terms have x dot, that is velocity. Assuming the velocity is not equal to 0, then mx double dot plus kx equal to 0, which is the familiar equation of motion for an undamped single degree of freedom system. So far, we have analyzed the spring mass system in a horizontal configuration. That means the spring mass system will be look like this. Now let's consider more general case of vertical spring mass system. This introduces additional force of gravity. The process of deriving the equation of motion remains fundamentally the same. Consider the configuration shown in the figure. Initially, in diagram A, the spring has its own free length L naught. When the mass M is attached to the spring, extends by an amount del St, that is deflection at static. At this point, spring force, that is K del static, exactly balances the weight W, that is equal to mass into gravity. Now we further displace the mass by a distance x. Now let me analyze the forces acting on the masses. Here the free body diagram shows the forces acting on the masses. We have the weight acting downwards, the spring force, that is stiffness into del static, plus the additional deflection acting upwards. Applying the Newton's second law, we sum the forces and set them equal to mass times the acceleration. We note that the equation will now give W equal to K del St. Therefore, we can substitute in our equation and cancel it out such a way that mx double dot plus kx equal to 0. This is exactly the same equation of motion what we derived in the previous slide. In the previous slide, the derivation for this mx double dot plus k is not clear to you. So because of that, I'm continuing in this slide. That is, we have to take weight equal to mg, that is further equal to stiffness into del static. By applying this to the Newton's second law of motion, what Newton's second law of motion states is the accelerating force mx double dot is equal and opposite to the force which is going to be acting opposing the acceleration. Additionally, mx double dot, the accelerating force, is further added with the weight which is acting downwards. So according to this free body diagram, let me explore, that is the forces acting downwards is going to be W plus mx double dot, which is equal to the forces which is acting upward is spring force, that is KL del static. So that we can substitute it here. Since already W equal to K del static, which will cancel on the both the sides. So at last we will get mx double dot plus kx equal to 0. We come to very important discussion in this lecture, that is we already having that equation of motion is mx double dot plus kx equal to 0. This remarkable result simplifies our analysis considerably, as this statement highlights the weight of the mass doesn't explicitly appear in the equation as long as we define x as displacement from the static equilibrium position. The static deflection due to gravity is already accounted. Now let's consider solution for this equation. The solution for this equation is here complex exponentials. Here omega n represent natural frequency of the system. C1 and C2 are constants that we will determine based on initial conditions, typically the initial displacement and velocity of the mass. Equation 2.6 shows an alternative but equivalent form of the general solution using sine and cosine functions, where a1 and a2 are once again constants. related to C1 and C2. A1 and A2 correspond to the initial displacement and initial velocity respectively. Connection between these two forms involves Euler's formula, which relates complex exponential to sine and cosine functions. This allows us to convert between two representations depending on which mathematically more convenient, but both the equations describe the same simple harmonic motion. The mass oscillates sinusoidally about a equilibrium position with a frequency omega n. The constants determine the amplitude and phase of the oscillation. Now, we arrived at the general solution for the motion of our spring mass system. Now, the crucial next step is to apply specific conditions to find particular solution that describe actual motion in a given scenario. These conditions are typically initial displacement, initial velocity of the mass. The general solution states x of t is nothing but a1 cos omega nt plus a2 sin omega nt. This equation contains two unknowns a1 and a2 that we have to determine. Let me apply the initial conditions. First, let's consider initial displacement. If we set t equal to 0 in this equation, then x of t is 0 is nothing but sine will become 0. Hence, sine cos omega n of t. Once again, here, since t is 0, cos 0 will become as 1. So, a1 will become as x naught. Similarly, when setting velocity component is going to be 0, the other hand, derivative of this equation will give a2 equal to x naught double naught. We now determined both the constants, that is a1 equal to x naught and a2 equal to velocity divided by omega n. Substituting these values in 2.16, giving us the particular solution. The solution describes with a1 is now replaced with x naught, a2 is replaced with velocity with the natural frequency, which is represented in this equation. Let's delve into the nature of this motion, which is characterized by harmonic. As the statement indicates, equations that is in the previous slides all represents harmonic motion. This means the motion described oscillatory, which can be represented by either sine wave or which can be represented by cosine wave. This equation shows yet another way to express the same harmonic motion. X of t equals to a naught times the sine of omega nt plus phi naught. This form introduces two new constant a naught and phi naught. A naught represents the amplitude of the oscillation, which is the maximum displacement from the equilibrium position. Psi naught represents the phase angle. Phase angle essentially the shifts the sine wave along the time axis, allowing us to match the solution to any initial conditions. This equation shows how to calculate the amplitude from the initial displacement. Similarly, this equation shows how to calculate the phase difference between the two waves. We have discussed the equations that describe harmonic motion. Nature of harmonic oscillation can be represented graphically as shown in the figure. The figure shows two common ways to represent harmonic motion. Figure A depicts circle diagram. Imagine a vector A rotating clockwise with a constant angular velocity omega n. This angular velocity omega n is our familiar natural frequency. The projection of this rotating vector onto the x-axis represents the displacement x of t of our oscillating mass. As the vector rotates, this projection oscillates forth and back, mimicking the mass motion. The vector A has a magnitude equal to the amplitude A naught of the oscillation. It's shown here with components A1 and A2, which correspond to the coefficients of the cosine and sine terms. Angle phi represents the phase angle, indicating the initial position of the vector, thus the initial displacement of the mass. Figure B shows the more conventional way to represent harmonic motion, a sine wave plotted against a time. The x-axis represents time and y-axis represents displacement. Notice how the displacement oscillates positive and negative amplitudes, mirroring the projection of this rotating vector in the circle diagram. Amplitude of the sine wave corresponds to A naught in equation 2.3 is represents the maximum displacement of equilibrium. Distance between two peaks of the waves represents period t. The period t is related to natural frequency, that is equal to t equal to 2 pi divided by omega n. Finally, the phase angle phi shifts the sine wave horizontally. If the phi is 0, the wave doesn't start at its peak or trough at t equal to 0. You can see how the rotating vector in the circle diagram represents correspond to the sine wave in the domain. As the vector rotates, the circle diagram helps visualize the relationship between amplitude, phase, and frequency, while the sine wave shows how the displacement changes over time. Let me explore the harmonic motion, which is, see here, the circle over a circle, the particle is moving. This particle is moving at a velocity v. When it is rotating in a circle, it will be represented in terms of omega, that is velocity divided by radius of the circle. This particle, which is rotating along a circular path, can be projected over to the graph, on which the graph represents x-axis, that is time domain, that is the t, while y-axis represents amplitude. This particle, when it is projected over to this space domain or time domain, then we can see this rotation is represented in terms of sine wave. Whenever the particle reaches the 0 point, the sine wave at 0 degree. Similarly, when the particle at 90 degree, sine wave reaches the maximum amplitude, positive amplitude, that is, when the particle reaches downside, the sine wave also reaches the negative maximum amplitude. This way, we can clearly understood the circular oscillation, that is the harmonic motion. In mathematically, we can represent sine or cosine wave. Sine or cosine wave, which is depends upon at which time the particle motion starts. In the previous slides, we have seen that the equation of motion for a vertical spring mass system is the same for the horizontal one. However, it is subtle but important different when it comes to calculate the natural frequency. Let's explore. The equation shows circular natural frequency omega n. It is the square root of the spring stiffness K divided by the mass M. This formula holds true for both horizontal and vertical system. However, in vertical spring mass system, we can express the spring constant K in terms of weight and the static deflection. As we discussed earlier, at static equilibrium, the weight equals the spring force W equal to K del static. Since once again the weight equal to mg, we can also write stiffness equal to mg divided by del static. Hence, this circular frequency becomes omega n equal to, instead of k you can substitute this, then mass will get cancelled. We will get natural frequency equal to square root of g by del static. This is our new expression for the natural frequency. In the previous slide, we discussed circular natural frequency omega n. Now let's introduce two related concepts: natural frequency in cycles per second, that is F1, and the natural period T. When the spring mass system is in vertical position, defines the natural frequency, which is measured in cycles per second, that is Hertz. It is related to circular natural frequency by simple equation omega n equal to 2 pi Fn. We get Fn equals 1 by 2 pi times the square root of g divided by del static. This F1 tells us how many complete oscillations the system makes per second. For example, if F1 is 2 Hz, the mass oscillates back and forth 2 times every second. Equation 2.3 defines natural period. The period is the time takes for one complete oscillation. It's the inverse of the frequency. Substituting our expression from the above equation 2.29, we got the time period equation. Time period is measured in units of time, typically seconds. Let us see how long each oscillation takes. For instance, if time period is 0.5 seconds, each oscillation takes half a second. Notice inverse relationship between the F1 and time period. Higher frequency means shorter period and vice versa. Now we have three ways to characterize natural frequency of a spring mass systems. One is circular frequency, another one is natural frequency in cycles per second, and natural period. They are all related to one another and also depend on the static deflection, del static, and acceleration due to gravity. We understand the displacement of the mass in our previous slides, but what about its velocity and acceleration? These are crucial for fully describing the motion and understanding the forces involved. Let me see. The displacement x of t is given by equation a naught sine of omega n of t plus pi naught. Remember, a naught is the amplitude, omega n is the natural frequency, pi naught is the phase angle. To find the velocity, which is the derivative of x of t, we differentiate x of t with respect to t. The derivative of this will provide you this equation. Therefore, velocity will be represented when replacing this form mathematically, we will get in terms of cos. We differentiate once again the velocity with respect to time. Therefore, we will get the acceleration, which is exactly represented omega square a cos omega t minus pi plus pi, which once again we can see that This can be represented as A naught sine omega t plus pi naught. So acceleration will be equivalent to the maximum when it is going to be in the opposite direction. We now have expressions for displacement, velocity, accelerations as a function of time. These equations allows to fully describe the motion of the spring mass system at any instant. We examined the general solution for the spring mass system. Now let's explore special cases focusing on specific initial conditions. First, consider the case when the initial displacement is zero. This means at time t equal to 0, the mass is at the equilibrium position. This equation shows the displacement for this case. It simplifies in terms of sine omega and t. Notice that the motion is described by a simple sine function. The amplitude is given by the initial velocity x dot divided by the natural frequency omega m. Physically, this makes sense. If the mass starts at equilibrium with certain velocity, its subsequent motion will be sinusoidal, with the amplitude determine how much initial push it received. Now let's consider the opposite case where the initial velocity is zero. This means mass starts from rest but some initial displacement x naught, which eventually give the equation of motion can be represented in cosine form. That is, the motion is described by a cosine wave. The amplitude is simply initial displacement x naught. This also aligns with our intuition. We release the mass from rest at a certain displacement. It will oscillate with that a displacement as its amplitude following a cosine wave. These two special cases provide valuable insights into the behavior of the spring mass system. They show how the initial conditions dictate the form of the harmonic motion, whether it is sine wave or it is going to be a cosine wave starting from rest at an extreme position. Let's once again I conclude, if initial displacement x of 0 is 0 at time t, we will get sine wave. When initial velocity is 0, then the harmonic motion will be cosine wave. Thank you.